Hello, my name is Danny Dries, and today I would like to talk about our recent paper, Deep Visual Reasoning, which is the idea of predicting an action sequence for task and motion planning from an image of the initial scene, such that ideally only a single motion planning problem has to be solved. Consider the following scenario where the goal is to place the yellow box on the red spot, which is occupied by the blue box. There are other objects present in the scene and the robot arms have to collaborate to solve the task. Such sequential manipulation problems are challenging since they inherently involve continuous and discrete aspects. Task and motion planning approaches address this by combining reasoning on a symbolic logical level with continuous motion planning, such as nonlinear trajectory optimization or sampling-based methods like RRTs. The symbolic level, commonly defined in terms of first-order logic, proposes high-level discrete action sequences for which the motion planner tries to find motions that either fulfill the requirements induced by the high-level action sequence or return that the sequence is infeasible. In this scenario shown here, there are about 500,000 discrete action sequences up to length 6 that reach the symbolic goal. At the same time, due to kinematic constraints such as reachability or joint limits and other objects that act as obstacles, the majority of the discrete action sequences are infeasible and therefore, many motion planning problems have to be solved to find a feasible solution. To overcome this combinatorial complexity, the main idea of this work is, given the scene and the goal as input, to learn to predict promising action sequences such that ideally only one nonlinear program would have to be solved to find a solution to the overall problem. More specifically, we propose a deep convolutional recurrent neural network that predicts action sequences for task and motion planning from an initial scene image. So basically, by looking at the scene, the network will predict the action sequence. We develop how this network can be integrated into the tree search of logic geometric programming. And the cool thing is that although the network has been trained on only 2 objects in the scene at the same time, it generalizes to scenes with multiple objects. A key aspect why this is possible is because we represent the scene and the goal in the image space. First, I will quickly summarize logic geometric programming, or LGP, which is an optimization-based approach to task and motion planning. The idea is, given a scene S, to find a path X in the configuration space of all robots and objects as the solution of an optimization problem. This path consists of k faces with length t. The number of faces is part of the decision problem as well. Now the important part, the costs and constraints are parameterized by a symbolic state variable s, and the time discrete decisions between this state are subject to a first-order logic language through action A, which are grounded action operators. The goal is specified symbolically by g. Then an LGP looks like that. The key difference to a normal trajectory optimization problem is that the discrete aspects of the manipulation problem are incorporated into the costs and constraints through the symbolic state S, like in a mixed integer program. But since this state variable S comes from a logic domain, it introduces more structure to the problem. The logic defines a decision tree where each node represents a nonlinear program. Solving an LGP means a tree search over a sequence of actions such that one reaches a leaf node of that decision tree and the corresponding nonlinear trajectory optimization problem is feasible. So far, LGP relied on lower bounds, which are simplified trajectory optimization problems to guide the search. However, if we remember the scene from the beginning, there are about 500,000 leaf nodes here. And the problem is that many actions in early phases of the sequence are feasible, therefore the lower bounds do not help much. To overcome this, if we could learn, given the scene and the goal as input, to reason about promising action sequences before checking them, the number of nonlinear programs that have to be solved could greatly be reduced. However, one of the big questions here is how the objects in the scene and their properties as well as the goal can be represented as input to the learning algorithm in a way that not only allows generalization over different object properties, but especially also generalizes over changing numbers of objects in the scene. Let us first define for the scene S and the goal G the set T as the set of all action sequences that reach a symbolic goal, hence candidates for a feasible solution or leaf nodes of the tree. With f of a1 to k, we denote the feasibility of the action sequence a1 to k. The first idea might be to collect data and then learn a function f hat that approximates this feasibility function f. However, querying this f hat over all possible action sequences and choosing the one where f hat has the highest value is intractable due to the size of t. Instead, we want to learn a function pi that decides whether an action ak at step k of the sequence is promising in the sense of there exist future actions up to capital K, which not only reach the symbolic goal, but the corresponding trajectory optimization problem is also feasible. All that conditioned on the goal G, the scene S, and the actions taken before. During the tree search, one would then follow at each step the action where pi has the highest prediction. It turns out that through a data transformation, learning pi can be framed as as a well-defined supervised learning problem, which I state here, but I have to skip details due to time constraints. One might ask what the difference of pi is to a goal-conditioned universal Q function. It is very important to understand that in LGP there is no clear notion of state. The symbolic state S neither contains all relevant geometric information nor takes into account the effects of the previous or future actions. To explain what I mean with that, look at this here, where each arm should grasp a box. Now, if in the future an additional action is taken, namely to place the blue box where the yellow one has been, it influences the trajectory of the past. While this is one of the major strengths of LGP, allowing it to solve impressive problems, it makes learning much harder since there is no clear notion of an intermediate state as required in Q functions. Now the big question we have not talked about yet is how the actions, the goal and the scene can be input to the learning algorithm in a way that allows generalization over multiple objects. Fixed-sized feature vectors are problematic in this respect. Given an action A, we decompose it into A bar and O, where A bar is the discrete action operator symbol, for example grasp or place, and O is the tuple of object the action operates on, for example box and table, if the action is to place a box on the table. The goal is similarly decomposed. We now can input A bar and G bar as a one-hot encoding into the network, since the cardinality stays the same, independent from the scene. The key is to encode the object tuples O in an image. This image consists of masks indicating which objects are involved in the action, as well as a depth channel that shows the relation to other objects. This is the key to both good performance and generalization to multiple objects, while the input size of an image stays the same, no matter how many objects are in the image. The network we propose consists of CNNs that encode the action object images and the goal image, as well as fully connected layers that encode the action operator symbols and the goal symbol. The resulting encoding vector is then fed into a recurrent module, which takes care of sequence prediction. Since the robot has only access to the initial scene image, this recurrent part implicitly has to learn the effects of the actions on the environment without explicitly being trained on, for example, to predict a future state, which is, as explained before, not really well defined. Now to the experiments. Due to reachability constraints, the two arms have to collaborate. Here the network proposes a handover solution and the first predicted action sequence is feasible. Handover solutions are only possible if the object is large enough. Since here the green box is too small for a handover, the network correctly proposes a different solution. During training, only 2 objects are present at the time. The cool thing is now that the network generalizes to scenes with multiple objects. Here we can see an interesting and efficient utilization of the 2 arms the network proposed to solve the task. It also knows when a single arm is enough, or can solve more complex problems with long action sequences in the presence of multiple objects. We also performed real robot experiments. One has to state here that we still need a perception pipeline to get the shapes of the boxes for the trajectory optimization, which also allowed us to use rendered images, such that we could use the network we have trained in simulation. Also here the network reasons about the geometry of the scene and directly predicts the action sequence required to solve the task, such that no search was necessary. Here it will do a handover. By the way, the ability of the system to perform handovers evolves from the parameterization of the trajectory optimization problem and is never explicitly represented. I kind of find the handover solutions interesting. Let's look at some plots. The plot on the left shows the total solution time over the length of the action sequence. Even for sequence length 6, the median is only 2.3 seconds with an upper whisker of 7 seconds. The plot on the right shows the number of nonlinear programs that have to be solved. As one can see, most of the time the first proposed action sequence is actually feasible. This means that search can basically be eliminated, since the network knows by looking at the scene which action sequence to choose. For sequence length 1 and 2, the network has 100% accuracy, but also for sequence length 6, with a median of only 2 NLPs that have to be solved. This is really cool, I think. If we compare that to LGP tree search, here shown on the right, one can see that this problem is actually hard for LGP, with solution times going into the thousands. For sequence length 4, with our network, it is 46 times faster, 100 times for length 5, and for length 6, even 700 times faster in median. Now this plot shows the total solution time over the number of objects in the scene. As a reminder, during training, only and exactly 2 objects are in the scene. Although the network inevitably makes some mistakes, the solution time barely increases for more objects, which I think is really cool. To conclude, we have proposed a deep neural network that predicts promising action sequences for tasks in motion planning from an initial scene image. Most of the time, the first predicted sequence is feasible. Although being trained on only 2 objects present in the scene, the network generalizes to multiple objects. An important assumption and therefore limitation of this work is that the initial scene image has to contain all relevant information, which means that there should be no total occlusions or other ambiguities. If you're interested in more details, check out the full paper, which just got accepted for RSS this year. Thank you.